worked together at Oracle and Sun since the early 90s. Michael is an alumnus of this fine institution.
Yes.
And has been working more or less in tools for your entire career. I think maybe some little side trips here and there.
Much of it.
And is the, often the lone voice in the corner of the room who talks to the compiler and the VM guys and says, "But how are people going to use that?" And so, people. People is the operative word. It's not computers and software. There are people involved. And Michael thinks about people and how they do stuff and what they do and how they do their jobs and what we need to support to do them. So I think this it is the last part of the course, so it kind of does look like an afterthought.
Always.
Just where it needs to be.
But at least there is a slot on the course. So I think this will be really interesting.
Much appreciated to actually have this opportunity.
That was on and it must have shut itself
I haven't
off.
plugged it in yet, so.
Oh, okay. It did work, so hopefully it'll work again.
Okay, let's give this a try now. Let's just change this version. Okay, good. Cool, actually works. Okay, great. Okay, well, thank you, Mario, for the invitation. Let's see, let me make one more adjustment here. Why is my cursor not showing? Yeah, that's not gonna work. Okay. Okay, good. Okay, so let's see. Let's okay. There's still a little operator error here. Okay. So yeah, thanks, Mario. I'm going to introduce myself a little bit more, just so you know where I'm coming from. That's especially important because I'm not a VM guy, so you've had a long time now to learn how a VM guy thinks about the world, which is almost as important as anything actually technically you learn. Is how do you think about the world if you were doing this or that? Okay, so I'm not a VM guy, and I always have that disclaimer. So anything I say about VMs, you should distrust. So who am I and what do I actually do? So Mario just said this, I think it was around 1993. We've been more or less in the same place. I've reported to Mario at least once, maybe more, lost track. It's all very fluid in a good lab. So we certainly know where each other's coming from. So I've had a very checkered career. 3 trips through school, and they were discontinuous by several years in each case, right? So each was a different phase of my life, starting with sort of really things that I was interested in. And then when I did my MS, I was actually thinking about programming, improving correctness of programs and stuff. And there was a language implementation system that had an advanced parser that wasn't just an algorithm, it was really a whole parsing system for languages. So I did a correctness proof on it. I thought that was really cool. And then I went off and did other stuff for 8 years, and then landed at Berkeley, working in Sue Graham's work, who at that time had been migrating from compiler work to interactive program editing systems work. And so I joined the group doing on that, and focused a lot on the human factors and how work actually gets done with such things. We were talking about that over lunch a little bit. In between there, I taught for 4 years in the computer science department down at Cal Poly, which was a very formative time. The students there are extremely smart. They all come in like with 4+ GPAs and stuff. It's a very hard department to get into. And I remember the single thing that was hardest teaching undergraduate programming was that they didn't seem to have very good tools. And so that kind of refocused me. And so when I did come to Berkeley, I came here with the specific intention of working on developer tools to make programmers more productive. Because it had seemed to me by that time that most of the subjects I had been studying in graduate school previously, my previous tour, didn't really help any programmers get their work done. So that's been my focus pretty much ever since. And in almost every project, I'm the tools guy, right? So, and here's just a quick sampling. Mario will remember some of these names from the past, but I've touched on a lot of different areas of tooling over the years, including some that we'll come back to. So you heard a little bit about the Maxine Inspector, I believe, and so that was my project before this. That was my first encounter with the VM world, I should say. Before that, I spent 3 years studying the HPC world, which I didn't know anything about, and before that, a whole series of other things I didn't know anything about. So part of my history is sort of starting a new project on something I don't know anything about, but with the stance that it's important to figure out how we help programmers get work done. So, okay. So here's what I want to talk about today. First thing I want to do is sort of do my review of the entire course that you've had so far from a different point of view. I can get away with this. The second thing is,
turn the camera off.
I want to talk a little bit about how I think about developer tools, and again, that will sort of emerge from this. But it's really important. I think that's as important as actually the technology. It'll tell you why I'm doing what I'm doing in the context of this work with Mario. And then Mario has given me license to rant a little bit about strong opinions about developer tools and the role they play and why we have them and don't always have them. And then finally, I'll get to some technical stuff and tell you what I'm doing personally about tool support in the truffle growl world, okay? And then maybe by then you'll be back on sort of more familiar footing. So, okay, so starting the review. So I went back and looked at some of Mario's slides, and here's one. Language user's dilemma. So I take language user to be a programmer. And so their dilemma is what? What does it say? A big team of implementation experts to build an optimizing VM. Well, as a language user, my question is like, how do I get work done? You know, where's my debugger? No debugger? Well, really? No. So I looked around Mario's slides some more, and then I found what looks like a solution. It says, oh, yeah, is it resolved? We say, yeah, it's really fast now. And I look at this, and I say, well, okay, let's reevaluate. I'm still looking for my debugger. Where's my debugger? You know, so that's my summary. Actually, no, here's one more thing. Oh, yeah, this is another one of Mario's slides. Here's a system architecture. Okay, so you've probably seen this, so you know, once you look at it, think about it a little bit. And now, if you're me, what comes to mind? Well, where are the tools? How do you use any of this stuff? What is a programming language? What is there between a programming language that sits there and runs and a person trying to write code? Okay, and so that's the sort of, okay, end of review. Okay, so the whole point is that when you think about VMs or any other language implement technologies, usually tools don't show up. And by implication, people don't show up. Okay, so that's my starting point. And you saw all the different kind of stuff that I've worked on in terms of projects. I had a wonderful opportunity, courtesy of the US government and DARPA, to think about this for about 3 years. During that time, I didn't do any development of my own. It was a project for DARPA in the area of high performance computing, like the big $100, $200 million machines like out at Lawrence Livermore and those things, right? Supercomputers. And Suncray and IBM were in a competition. This particular project uniquely said, we want to take a left turn here in our next round of procurements. This was 12 years ago. We want the next generation of machines. By then the target was petascale, petabyte, petaflop type machines. We actually want them to be more productive. Now, what does productive mean? Well, that was one of the problems. Nobody had any understanding of what productive was. So in the HPC world at that time, for many years, a proxy for productivity had always been what they call speeds and feeds. How many floating point operations per second are potentially available? And what is what they call the bisection bandwidth? How fast can you get how much data in and out of the machine? Now, my suspicion is that the latter was really because their number one problem was checkpointing, because their stuff was so unreliable. that if you have stuff that runs for a very long time, you spend a certain amount of your overhead checkpointing your progress so that you don't have to repeat it if you get a crash. So one of those little secrets. And the challenge for them, okay, supercomputer petascale, but part of the challenge was to come up with a notion of what productivity means, because they admitted they didn't know what it meant, but we want more of it. So they set an arbitrary target of 10 times more productive, which was our mantra. So design a supercomputer, which means all the way from chips to system, maintenance management, and we want to be able to get more work done with it. Well, that means that somebody has to go try and figure out how you get work done with it. That was astonishing. That was the high astonishment factor at all, that they were interested in doing that and willing to put some money into it. So Sun, actually, as the leader in the area of productivity, put together a series of cross-functional teams, and I was on one of them. The core productivity team. So we were one of 4 cross-functional teams, and by that means that if you were to look at that normal system stack, what with chips at the bottom and all this other stuff at the top, a cross-functional team has a responsibility at every single level. Okay, so our job was to investigate systems at every single level and try to understand how we would, in principle, achieve this goal of making a supercomputer 10 times more productive. And even more interestingly, the person who hired me to do this had an interdisciplinary team that was quite a pleasure to work with. So for 3 years I was the only person who was actually a computer scientist with a software engineering background. I was working with a physicist. I mentioned an expert HPC programmer, a very wizard at writing the kinds of programs that it takes to run on these supercomputers. It's unlike anything you know. And a cultural anthropologist. What? If you're going to study how people get work done, that means you have to study people. And if you want to study people, that's what cultural anthropologists do. It's this funny mishmash science of psychology, sociology, culture, and stuff I can't even remember. It's a synthetic science. It was created in the last century. So that's, and this person, Sue Squires, was a practicing cultural anthropologist. She didn't teach, she didn't do research. She worked for big companies and studied these kinds of questions. She did early work on cell phones before there were cell phones. She studied breakfast foods for busy families. I mean, you name it. She had kind of got out and done field work. So this is pretty wonderful stuff and quite interesting. So I wanted, yeah.
Is the physicist in this case your end user?
No.
Is it a physics software program, or is a physicist someone who understands?
If somebody who understands the world of HPC,
okay.
Most of the HPC cycles go to people doing big physics at the Department of Energy.
Right.
But not exclusively. If you look at the customer list, you'll see that Department of Energy is only one of them. Okay. And
no such agency.
I'm sorry?
No such agency.
And no such agency out there somewhere beyond the fringe, the kind of place where when Cray sells them a machine, they never see it again. Yeah, they were also customers. And as it turns out, had very, very different requirements than the DOE people. Enormously different. We can talk about that later because it's off topic for me, but
They're all
not
fairly
that much off
they're all
topic.
fully understandable now.
Yes, let's just say that one part of the project was to try and evaluate in advance how good a machine would be. That's one of the problems because you can't build a prototype of these machines, right? You spend $100 million to build one. You really don't know. So they had a whole sub-area of work was to build benchmarks that you could simulate that would tell you something about a proposed architecture at this scale. And they had to be scalable. They had to really scale out. And so a new round of these things were developed as part of the project. Some of the parts we collaborated with IBM and Cray, and the other parts we competed. The productivity teams were collaborative. We worked together with the others because our job was to define productivity. The synthetic benchmarks, let's just say that there were a series of them that were all quite understandable, and then the last one was graph partitioning. Just going, what? Okay, the DOE doesn't do graph partitioning. So, moving on. So let's look at some models, some of the things that came out of our final report. To just summarize what I think we learned about the topic at hand, and I just happen to have this in our report. So let's, models of a customer HPC system. Just for a little bit of context, here's what a software project typically looks like in that world. The software takes 5 years to develop, really, to start testing. This is expensive software. A typical project has no more than a few 100,000 lines of code. It's very difficult software to write. And then it is in use typically by customers, and the customers tend to be scientists around at the DOE and government labs. The software is normally open, so it's shared by people at universities. They did open source before it was a thing, for example. Government software was mostly by definition unclassified and available. And then people use it for their research and has continued testing, although their notion of testing is different than anything you would recognize. And then they tend to be retired when nobody's willing to fund the next port. Did I mention porting? Okay. A supercomputer, they tend to be one-off, unusual. And they tend to also go through phases of different architectures. So when we started the project, clusters had just become big, which replaced a previous generation of purely vector machines, which replaced I don't remember what. So the fashion changes. But even within that time frame, the lifetime of a supercomputer is about 4 years. And after 4 years, they're usually not useful enough to be worth the electricity to run them. So you port these software. So do the math, how many times a piece of important software gets ported. And it may be from a vector to a distributed memory cluster. So think about that. So it's expensive software. So when you look at this diagram, you can say, well, where are the tools? Well, there's tools everywhere, right? Everything you see, every task that gets done has both people and tools in it. You can't do any of those things on that list without tools. So clearly tools are a big part of what they do. And one of the things I learned in my first year was that the HPC world in general of government-funded labs has a seriously broken model for tools. And I wrote a paper about it that said, this is really screwed up. But I tried to identify the causes, and you'll see that when we come to one of my next models. Okay, so that's one model. How do people model computer systems? So here's another common one. This looks like kind of like Mario's. This is kind of a cartoon version of a normal system architecture. The one that we had for our petascale computer had about 10 levels in it, okay, if you will. It was very complicated, but this is kind of representative. Notice that I kind of sneaked in that one called development environment. Normally it's just application, system, software, hardware, something like that, right? So again, classic how computer systems people think about computer systems. It's a systems approach, and you have a model. So where are the tools? Well, like I say, I put it in here. So that, to me, then implies that that's where people go. So when you look at this, though, think about my colleagues. Okay, so one of my colleagues, we collaborated with other people around the project. So one of the colleagues who was working on sort of the memory model stuff, he really cares about the bottom two boxes, and he had his own view of the world. Our HPC expert programmer, well, he cared about the top two things. So everybody has a different take on which piece of this really is important to them. Right? So that's the other to think about for this particular model. So there are different people with different concerns, and this helps you map that out, those boundaries on the different parts of the system. Most people usually only care about 2 levels. Here's another model, okay, a little bit different. This is a software engineering workflow model as it applies to the kind of organizations we were talking about. This is very different. Notice that it's got 3 levels. So at the very bottom is what you would recognize. In other words, somebody with an objective and they need to produce a solution and write the code until it works. Okay. And there's lots of those. That's what we normally think of in computer science, is a person, even with the tools. There's some person there, they've got some tools, they have some workflows, and they produce a piece of software. But notice that most projects actually have more than one piece of software. And at the project level, people think about it differently. That's what managers up there, they think about the overall project. And so they're making trade-offs and allocating resources of people and money. And they're looking at iterations. They may be doing something over time, and they may replace software by one thing with another. They've got maintenance issues. All of a sudden, reuse becomes important. So if you're a programmer at the bottom, reusing software is not a thing because it takes extra work. So most people rewrite everything from scratch, right? And anybody who's the smartest programmer around, which is most of us, is going to say, oh, I can do better than this, and they'll rewrite something from scratch. Reuse normally gets imposed organizationally as a budget, as an overall budget optimization to say, no, we can't afford to keep rewriting everything. We've got to reuse the parts. All successful stories of code reuse I've ever seen were imposed by some structure. So that's the kind of thing that goes on at the project level. When you go up to the big organization level that operates many projects, like a big lab or a university or a big company like Oracle, you have an overall mission, and projects come and go. And you have to then allocate investment very strategically in these missions, okay? But they happen on a different time scale. And that's the important thing here, different time scale. And in every case, you're allocating resources. In every case, there's ways of thinking about it. And if you are a person down there writing code, you, in a sense, are participating in every level, even though there's decisions being made, okay? So this was one of the issues I identified with the developer tools in the DOE labs, was that any individual project can't afford to invest in tools. They don't have the money, or they can't take the time to build them. So normally at project level, you might want to invest in tools, but even then that doesn't always happen because it's expensive to develop tools, especially if you're working on platforms that change out from under you every 4 years. It's a problem. So you'd say, well, at the organizational mission level is really where you should be thinking strategically about tools, because you want to make your people more productive and you want to sort of nurture them over time. And in the case of the DOE labs, the issue we found and identified and reported on in a paper that I wrote is that the US government wasn't funding the tools for the labs. They would buy machines. They would buy big, expensive machines, but there was no budget for tools. So what you found in practice was down at the project level, people were stealing time and resources without telling anybody and using them to try and develop the tools they needed. This is a fact, okay? Okay, so there's a model, and there's people, and there are some tools if you know how to ask the question. Here's Sue Squire's model of the world. This is a cultural model, if you will. And notice that an anthropologist would say that every person lives in many cultures. As an individual, you know, you're a computational scientist, but you have actually responsibilities and obligations and a role to play in every one of these circles. Somewhere out there, you're a citizen, okay? And one, for example, in her world, one characteristics of a well-performing environment is when the goals of these things are all well aligned. When you have them not aligned, you also run into really interesting sets of problems. I'll leave it to your imagination what happens when different parts have priorities and alignments that go in different directions. You read about it in the news. So where are the tools? Well, this doesn't talk much about tools, but where are the people? Well, this is about people. So the example I just mentioned of why the DOE labs seemed not to have the tools they needed is the culture of the US government. And it's not just that they're incompetent, it was the cultural issue. People in Congress who vote to allocate $100 million for the next great supercomputer to one of the DOE labs do that because you get a lot of exposure for it, and you get a lot of press, and you get pictures. You don't get pictures for tools. You don't make the press. You know, nobody sort of cheers you on for building the next great thing, like the world's fastest supercomputer, right? There's this arms race in supercomputers, and so if Congress approves the next great one, it's like, this is great, it's in America great, right? We're building the next great supercomputer. But yeah, better development tools, doesn't happen. So it's a cultural question, and that was really the root cause there. So we say, well, we kind of take a synthetic view. If you're looking at the whole system, you really have to look at the whole system. So a synthetic view says, well, an actual HPC system installed doing work looks something like this. At least this is one model of it. Notice there's people there. And there are tools there. There's still a development environment there. I think there's a bug in this diagram. The order is probably wrong in some places. You could argue about that. But tools are there. Tools are a necessary part of this, right? I gave a talk at the JVM Language Summit a couple years ago, and I introduced myself as the user interface guy for their technologies. I said, you guys all make code run fast, but it's nothing if you don't have a UI for it. And the UI are tools, editors, debuggers, you know, all that kind of stuff. So you should be nice to tools people. So it's a critical part of what goes on here. Okay, so to summarize kind of what we came at, just for completeness, here is our model of what we think is going to take to achieve the goal for DARPA. We didn't get the follow-on contract, so we never carried on. But the way to read this picture, this is kind of a two-dimensional now spreading out of the previous picture plus the goals we got, the targets we got from DARPA. And they broke out the productivity goals for us into programmability, portability, performance, and so forth, okay? And so our team, our greater team, the whole team really came up with these as the key ideas we were proposing. So there's listed as 5 design requirements we felt that were important to meet those goals with sort of the lines there connecting them. And the 5 major innovations we felt were necessary, some of which we felt pretty strongly we had something to say about, would it take to meet those design requirements? So this is one view of the chart of how we expected to meet DARPA's 10x productivity challenge for the whole entire computer system. And you will see that languages and portable tools is one of those things. Very, very important. Okay, so that's how I think about it and what I learned thinking meta about it for those 3 years for DARPA, where I didn't have to write any code. Our job was to just make a case for what it's going to take to get a huge jump in productivity. And I think the real world is not that much different than HPC, to be honest. Yeah, Peter?
Specifically, for applying to DARPA grants,
Yes.
to me it seems like the biggest difference between working on computers and working on tools is that it's easy to say how fast your computer's going and much harder to say how good your tool is.
It's understood, and that, as I mentioned, one of DARPA's tasks for us was to say, and by the way, all 3 of you vendors should work on a good definition and metrics for productivity, and you should work together because we need a good operational definition of productivity. I can't say that we succeeded very well at that, to be honest. It's very hard, yes. It's about people. And it's so contextual. Again, that's why we have an anthropologist, right? So how do you measure in isolation how productive a tool is? Yeah. Whereas being the fastest supercomputer is completely objective. They know how to measure that. Is it useful? Not particularly. Because if you ask the HPC people about their the megaflops or petaflops they can get, they say, well, how many of them do you actually use? It's called utilization. Usually not very good. Yeah. Because the technology isn't good enough, programming technology. Yeah.
Wouldn't people argue if you leave this to the private sector, languages with better tool chains normally wins the war?
Normally,
I mean, if you have
wins.
Yeah, I mean, if you have private computations.
You would think. But here's the question to you. What do you think the average amount of money per programmer most companies invest in software development tools? Just a thought. Yeah, pretty small.
But the thing is, they will discover the productivity by using it. So then it's non-intuitively defined by the economics.
Yeah. It's a great question. You really hit the core of the problem, right? Why don't we invest more money in the tools for our programmers?
There's no economic incentive.
Well, doesn't it sound like there should be if they really made them twice as productive?
It's a long-term economic incentive.
Part of it's the long term. Again, that's that level of organizational, right? It doesn't make sense in the small. It makes sense or at least at the organization level, if not the mission level.
That make the government the right stage. That the government's designed for long-term.
So in the HPC case, the fix would be for the government to fund tools. Yes, exactly right. It's a great question though. Why it doesn't happen elsewhere? I mean, we can all spend our own theories, but in fact, it really doesn't. People just don't invest in tools for programmers much.
Yeah, I'm curious, if this is a recurring issue and people have seen this over and over again, then why isn't this now factored into project budgets before proposing a budget?
Great question, I don't know. Other than just the usual cynical things we say, right? For starters, management probably, I can guess, management don't have confidence that tools actually will make the difference. Would be my first guess.
Are there clean studies that show objectable numbers of tools doing X quantity factors better?
It hasn't been a fashionable area of research for a while. There's some great work done in this at Bell Labs about 25 years ago, and they learned a lot of really interesting things. For example, about code reviews were very wonderful, big then, and there was a whole research literature on how the right way to do that was. And they did some empirical studies on code reviews, and it was very revealing. The high level bit of that work. And the reason I know this is the chairman of that group was the physicist I mentioned here, did empirical software engineering at Bell for years. He said the high order bit is, will the code be reviewed or not? And if it will be reviewed, then you get a very definite productivity increase. And if not, you won't. That's empirical, and so there have been some small workshops. For years there was one called the Empirical Studies of Programmers. It's not happening anymore. And there have been other related ones, but it's generally not a particularly well-funded area of research. Just doesn't. It's hard to ramp up the resources for it. So I'm gonna move on here. So this is the end of my here's how I think about it as objectively as I can say. Now, leaving objectivity completely aside, is I want to express some opinions. Okay, so we don't have it all. Okay, we have lots of languages, but usually when they show up, they don't have tools that come with them. it was a very long time before there was a working debugger for Java, for example. And a lot of the dynamic languages now they don't have debuggers, and people sometimes write them, they don't work very well. So what's that about? You know, and when they do arrive, there's usually, they're not as great as you would like. So there's a lot of compromises. So here's some typical trade-offs, let's just say for debuggers, but more generally for anything that relies on runtime information, is that there are at least one of these compromises will show up, okay? You know, either you can't be fully optimized, or there's certain, really there are cases where you can't use certain functions if you're debugging. Sometimes you have to ask compilers, the compiler writers, to do heroic efforts that they don't want to do to sort of provide stuff. Or you got to run in a special mode, you got to restart your program, you can't debug if you don't have -G on, whatever it is. So why? Well, why do we make all those compromises? So that's one of my complaints. We don't really have what we want. We don't have full service tools all the time. And it seems to be getting harder. Well, there are some reasons why it's harder. The challenges are getting worse. First of all, debuggers famously, by definition, they cross abstraction boundaries and do things that you went to a lot of trouble to make sure couldn't be done when you wrote your software, right? And so that's an issue for any debugger. It's sort of built in. And you know, platform dependency, they're not as portable as you'd like. And you know, one of the fundamental disconnects is that if you're a hot compiler engineer, your job is to get rid of information you don't need as fast as possible in your pipeline, and it's almost always exactly the information a person needs when they're debugging the code. I could go on about this. Actually, there's a journal paper about that very topic. It's a real problem. It's a real trade-off, right? And you know, all that. And if you do want that information, you know, the standard for native code lately has been, you know, well, several decades now, is you got to have a separate thing the compiler outputs and, you know, dwarf format that helps you reconstruct the state of execution. But you're kind of on your own if you're the debugger writer, and getting it right is tough. And in optimization, it's even worse, okay? Because again, the whole point of optimization is to get rid of information that's not necessary for the result. There have been lots of PhDs written on debugging optimized code. I know personally 2 of them. They were both came out of Sue's group, like 15 years apart. It's just not a problem that goes away. And now then, the world of dynamic optimization, oh my gosh, you know, how do we figure it out when things are being optimized on the fly? So that's my second rant. It's hard. And finally, there's this mindset. And you know, one of the root causes for all this is that if you're, and I've alluded to this in the way I speak about it, if you're an engineering, compiling an engineer, you make an assumption that basically says that machines are expensive, and so we have to make our code run as fast as possible, so we use less machine time. And so what do you focus on? Well, you focus on benchmarking, make things fast. Okay, that's absolutely it. Now, if you're me and you're working on tools, well, you make an assumption that people are expensive, okay, that their time is what's important. And therefore, you focus on human behavior. You might imagine it's kind of hard to collaborate across that sort of boundary, that gap, if you will, of concerns and priorities and assumptions. So at the end of the day, you end up with people that, you know, don't have the skills to do the other person's job. And part of what's come out of that then, yeah, is the disconnect between the two worlds. Okay, we'll see that a lot. So my personal experience with this, of course, being a tool person, I've almost always been around performance people. And so I have certain, and not just performance, but others, but I have certain ritual arguments that have played out over time in the several decades I've been doing this. So for your entertainment, here are some of them. Okay, ritual argument number 1. This is a quote from a CACM article, which was actually the main technical journal at that time, that says how tools should treat programs for the benefit of people using them, right? What's the viewpoint? Well, they're not really telling what it says here, okay?
Hi, we've got the room, I think, at 3. Do you, wait, you have it reserved?
I think so, yes. Can you double check?
Okay, so we were just talking about these guys over lunch, Teitelbaum and Raps. They argue that, yeah, it's actually a hierarchical composition of structures, and all the tools should be like that, and programmers should think about it that way. And like I say, this original argument, well, no, they actually aren't. That's just not true. MLVV, that's me. Okay. And but this keeps coming up over and over and over, right? I mean, that's why people think that structure editors were a good idea. And these guys did the original important structure editor. And a decade of experiments with them, usually only by people who had no choice, proved that they really weren't all that great. So here's another one. This actually is more personal. On a project I was on at this time, is I was The guy says, well, we're building a really advanced tool for really smart people, so therefore it's okay that it's really, really complicated because these people are really smart. And so the focus was on features. Really, you could do all this amazing stuff. Well, here's my point of view. Well, actually, no, we're building tools for busy people. Their time is unable. Therefore, we should invest in making it easy to use. It doesn't matter whether there's. Okay, so that one has come up over and over again. Here's another one. The most important thing is to make the language run fast. We'll build the tools later. Yeah. So that's my response to that one. So I could go on, but that's 3 typical ritual arguments you get when talking across this gap between the people who worry about productivity and the others. Well, it wasn't always this way. There were languages that had tools with them. It was kind of understood. And each of these 3 languages in its own way made a contribution in the area of good tools for programming, but it was simply understood. There was no such thing as separate debuggers for any of these things, for example, okay? In addition to those 3, there actually are other programming environments you've never heard of. There are just systems that have their own, like LabVIEW, for example, if you've ever seen that. It's all kinds of stuff that where you, and the distinction is they're programming systems. They're not just a programming language. And so Dick Gabriel's paper that I mentioned is full of a lot of deep dive on some technical issues, but at the bottom he sort of observes that shift in focus away from systems to languages in the research world changes your focus. If you only think about languages, you think about sort of rarefied semantic models and performance and stuff. But if you think about a programming system, you think about work getting done. Okay, so so there's a lot more history there, but let's just say, what can we do about it? So right now, I think we can have it all, and that's what my technical work has included here in the last while. And I'm going to get my bottle of water for a second. Still getting over a cold. Voice is only good for 10 minutes at a time. So 2 big ideas that I believe will allow us to actually have it all. You know, tools that work fast, no compromises all the time. Okay. So here's the first one. Okay, look at your language implementation platform and build the hooks for tools right into it. Okay, and the specific piece I'm focusing on is execution events, where you're about ready to execute something and you're in this particular computational state, or you just did it. Okay, but build it into the platform in such a way that instead of working at cross purposes with optimization, that you are part of the optimization. Like if you're a martial artist, blend, okay, become part with it. And do it in such a way that there's not a lot of extra work on the part of the language implementer, okay? So that you have this available all the time. So deep into the platform, and really rethink this notion of how we connect tools into runtime. So again, focusing here on runtime information, making it available. So that's the first one. Build it in, make it fast. And then build out tools and build out the core of the tools in a language independent way. We call them language agnostic, that they provide the same service whatever language you implement. And if you do that, and if the language implementers provide the little extra bit that's needed, then they'll actually have a working debugger before the language is even finished. And how would that be, right? Or maybe profilers, or maybe other things that we build. So always available extends, backwards across the release barrier right into the development process itself. Okay, and at the same time, we want there to be an API that allows external people to add new tools to do more kinds of analysis, both for research or other products, sort of related projects. So those are the big ideas that have been guiding what I've been doing now for a couple of years. Truffle and Growl represents a really interesting opportunity in this respect. In the sense, it's a complete reversal of what it looks like to build tools for native code-based environments, where reconstructing the execution state is really quite a challenge and often impossible. Here, the basic execution state is an AST interpreter, which is very straightforward. And even better, it's expressed completely in Java, okay, a high-level language where we actually have a lot of facilities available already. So it's just big data structures. I mean, the stack's there, the frames are there, everything you need is there. Now, that's the first most important thing. It's really a clear execution model. And second of all, the optimization, okay, the optimization code in Truffle is language independent. It's all about tree rewriting and specialization, okay, and then aggressive inlining and all the stuff you've heard about, okay. So make sure that the tools just basically participate in that because it's actually an advantage. Turn a bug into an advantage. And finally, and this is really the trick, this is the one thing that makes this all possible, is that for its own purposes, the platform knows how to de-optimize. So all that aggressive optimization that's done must be de-optimized so that you can have access to the execution state simply for the purposes of the speculative optimization. It's part of the architecture of the system. So now you don't have an externally imposed requirement from a debugger or other tool that says, oh, by the way, stop everything, I want access to the execution state. We're actually now leveraging kind of the internal power of the platform itself to do that as needed. So the debugger, again, becomes a participant. So a debugging event then looks like that. And well, let's just go on from there. So that's the real thing. So the blend is something I've described is to say automate as much of this as possible. So just sort of build it right in the first place. Here's the case, breakpoint conditions. Okay, famously, conditional breakpoints slow system zones enormously. Okay. The trick though, and this was actually done in the Smalltalk world, Mario knows this well, was to, well, just rewrite the code and then feed it back into the runtime and the way you go. And if you have an aggressively optimizing runtime and you attach it in just the right way, it becomes part of the program. So breakpoint conditions now run as fast, when fully optimized, as fast as any of the other surrounding code. So we've completely reversed the issue with breakpoint conditions. So a long-running program with a breakpoint now can have a condition at very little extra cost, no more than the actual cost of the expression and the framework costs. So all the framework costs of propagating events has very close to zero overhead in terms of runtime speed. Okay, there's almost no speed because the optimizer basically will inline all that stuff. And if you have some machinery there's nothing attached to it, if you're not listening, it will get inlined away to nothing. And you'll simply have no machine code generated at all. That gives us the option of having all the stuff empowered all the time. It's always available. And that's really where we're going. And finally, I mentioned the API. There's some stuff for that. So let me talk a little bit more about how it actually looks inside the system, what the abstract model is. So back to some pictures, they're more fun. So here's an AST, and there's a node of interest. So let's just say that's a node we care about. It's a piece, it corresponds to a piece of source code. Okay, so this is a conceptual model now. We'll talk about actual implementation sort of next. Okay, so here's some of the basic abstractions around this. Okay, first of all, there's this notion of a probe. So this is back to my electronics background when I was a hobbyist. A probe is a place where you can connect to get events. Events are available here, is one way to think about it. Okay, there's just a place you can connect. So that's attached to an AST node, and it says, okay, interested parties can find out what's going on at this node. So we'll call that a probe. And related to the probe is a separate mechanism called a tag. It's an annotation. It's a dynamic annotation. It's not part of the AST. It's not part of the type system. It's not part of the language. It's basically an annotation that's there whose purpose is to configure the behavior of tools. And the typical way to do that, the most common one, is to say, oh, this node is a statement. Okay. But it's not a statement in the grammatical sense, like this is a statement in the grammar. We're not being driven by the grammar. This annotation says, any tool that cares about where statements are should treat this node as a statement. In the debugger, that means if you're stepping, this is a place you want to stop. It's a critical distinction to have the tool behavior be configurable outside the engineering of the AST and outside the grammar and the parsing structure. I learned that the hard way here on the editor. Okay, so the tags are this sort of external configuration mechanism. Okay, so execution events then at this place that's been notated as a statement. Again, there's sort of this before and after. You can say, I just about ready to execute this statement, or I just executed it, and maybe here's a result that came from it, or something like that. Okay, so that's an event. And an instrument basically is the thing that connects then a probe with a tool that really wants to hear the events. So so I'll call that an instrument. And again, it's just an agent, if you will. It's the agent of a tool. All right.
Sorry.
So that's the first thing. And again, you should be able to attach as many instruments. You should have 3 different tools if you want, listening to the event stream from any one place at a particular statement. They should be operating orthogonally. So you could be statement counting, but you could also be debugging, and you could be doing anything else. So that's kind of the rough idea. And finally, and this is again the most important thing, is that optimization should apply to this whole framework. Okay, so everything here gets optimized as much as your actual end user code. Okay, so that's a conceptual model for what we want to accomplish. Okay. So let's talk a little bit of engineering now. This next diagram, these are actually nodes in the concrete data structure sense. Okay, so here's an AST. Okay, and notice now I've pushed down my blue in there, that node, and the important thing to notice about that is that there's a wrapper. Now, a wrapper is the way that we intercept events. We intercept them by sticking another node in the tree. And that node's job is simply to get the requests from the parent and then notify the instrumentation system that we just got a before event, and then delegate the execution of that down to its child, and then do the reverse when the event returns. Okay? It's important that the wrapper be part of the language because it has to be a type that can fit into the tree, right? So it's a language type. And then there's this second node over there, I call it a probe node. It's the agent for the instrumentation system. Its job is to manage instruments and delegate flows, and you can dynamically add and remove instruments. So all that gets handled by this thing called a probe node. It's actually a node, and it plays by the truffle rules, which means it can get optimized. Now here's the real ringer. You could be working along with your tools and doing all this stuff, and then truffle, without telling you, can all of a sudden clone this tree. And now you have two different data structures that represent the same piece of running code. So what you thought was statement 3 now actually isn't actually a node, it's two nodes. They're both statement 3, executing in different contexts. Happens when you inline, specialize differently, that sort of thing. So how do we do that with our tooling? Okay, well that's a problem when you get a clone. So we have to sort of understand that. And a clone, again, just to review, you probably heard this, it's a deep copy of all the things that are actually truffle nodes. So in this case, both the wrapper and the probe node are deep copied. And then we have to manage them somewhere. We have to track them. And the way the tracking done is that this thing called the probe now actually goes and sort of tries to figure out when you get cloning. So it actually knows that it corresponds to statement 3, and it keeps track of all the nodes that are executing statement 3 anywhere in the system. There could be any number of them. Okay. Which means that when you want to attach an instrument now, it gets a little more complicated. You say you instrument to this probe, and it actually has to go and modify the chain in each one of those things. Okay, so it starts to get kind of complicated, and there's a lot of objects here, and that's the basic idea. Okay, right now the current implementation, and I'll come back to ways in which it's changing. But again, the overriding principle here is that it's just part of the AST. To the optimizer, it looks just like any other code. It will get inlined. It will get optimized. It will get speculated on. It will get restored. All I have to do is know how, if I put in a debugger breakpoint, to know how to sort of say, oh, de-optimize me because I want to do something now. So that's how we get inside the system, if you will. How's our performance? Well, it's pretty good. The Ruby paper, if you happen to read it, was handwritten example of putting those wrapper nodes in to see if we could get truffle to basically partial evaluate them away, and the answer is yes. And so the runtime overhead was asymptotically 0 when things were running in the fast path. So this was pretty successful and encouraged us to go ahead and build out the more general framework. Ruby has a built-in mechanism for attaching trace functions anywhere you want in the program, and so our first measurements was to see how fast we could do that. Ruby has a number of highly optimized implementations. Every one of them falls down badly when you turn on tracing, because you have to go and sort of intercept the events. And in traditional compiled environments, that's really tough. It's like the breakpoint condition problem, same problem. We were able to demonstrate that we could do set trace functions without any loss of performance. Again, once it starts running, gets optimized back into the fast path, it's just like as if you had handwritten it. And so we could actually compare the compiler graphs and say, we're getting the same code as if you had actually just rewritten the program. So that's really a good validation. So very encouraging results. Limitations, well, there are some limitations. For one thing, the early prototypes eagerly went into the ASTs and put those wrapper nodes in. That turns out to expand the trees a lot, especially if you're not really going to need it. So if you want to have it always on, then you need to be a little more careful about your object allocations. And so we're actually rewriting the low-level stuff to make it more lazy. It will still look the same, but it will be more lazily instantiated, and the idea is to keep the object footprint down a little bit lower. The performance characteristics should stay the same, other than the delays. When you sort of start something up, you may need to do a little more allocation, but at the end, we'll really reduce the footprint a lot. Okay? So I mentioned that the language implementer doesn't have to do much. So just here's a real quick summary of what they do. They just basically, first of all, need to distinguish which nodes correspond to pieces of the program. That's the most important thing. This node corresponds to a statement. If you looked at some of the examples in the other papers, you'll find lots of other nodes that do complicated things that have to do with the implementation, but they don't directly correspond to a piece of syntax. So identify those nodes, and then tag them and say, well, what interest should a tool have in this? Well, this is an assignment, or this is a statement, or it's both. And there's a category for those. And so the implementer needs to do that. And then finally, there's just a few basic methods that are extra. And the extra one of interest really is eval, where you can say, take a fragment of code and evaluate it. Most dynamic languages already have eval built in, so it's probably not a big problem. It's a little harder to add the ability to eval at a frame in the middle of the stack, for example. A lot of languages aren't prepared to do that because that doesn't happen at runtime. But we've been able to sort of make sure that happens. And that's kind of it. There's a few other small things about how do you visualize, what's the value look like if you want to turn it into a text string. The debugger needs to do that. So that's it. If you're a language implementer, you do that. That's the price you pay for a debugger. So we think that's a pretty good value proposition. Caveats, well, okay, I've already mentioned the implementation is changing. It was prototype code. There's been a big architectural change. We now have a set of API frameworks that include everything, so things that were prototypes are being folded into that new. I mentioned that probes are now kind of virtual. And again, there's this focus on how the relationship between a place in the program, we call that a source section. So that needs to be cleaned up. So we're working on that stuff. So what have we built? Well, first of all, let's sort of look. This is the ecosystem, if you will, that we built out as this project has progressed. I'll call this the tool ecosystem now. So at the bottom is Graal, Truffle, and instrumentation. This is actually already progress. The reason that's progress is that instrumentation used to be a separate box, okay, in the prototype world. And after a recent round of work with the framework APIs, which are new, instrumentation now is buried deep in our code base and buried, so it's no longer useful to distinguish instrumentation from the rest of the system. That's a victory. That's sort of the enabling thing that we've done. Okay, things we've built with it. I mentioned that Ruby does this trace function thing. Our R language implementation, R has a requirement for a shell that has stepping. So it's not really a debugger, but you can kind of step. And it turns out that that's something that we were able to implement with the instrumentation framework with almost no extra effort. So that was a victory. So those are internal kinds of things. We have some external collaborators. I'll say a little bit more about some of them in a minute. But the folks at Irvine did a profiling on their Python implementation. Let's see, the folks in Lugano, that one's just kind of starting up. They want to do dynamic program analysis. I'll be meeting with them next week. The King's College folks, they're doing kind of front-end tools, front-end editors and visualizers and stuff. They're particularly interested in the multiple language environment. And we'll see actually some example of that in a minute. Okay, so these are all people who are not part of Oracle Labs who have been using this kind of for their own projects. I mentioned also the debugging API. Now that's again just a service, does a lot of basic stuff. And for testing and internal use, I built a command line debugger that looks vaguely like an old GDB debugger, but nobody uses that stuff anymore. Anybody ever used a GDB command line debugger? Oh, good. All right, so I'm not that old. Okay, cool.
There's no better tooling.
There you go.
I think they had to for my claim.
Okay.
There's really no good IDE for C.
I'm sorry?
There's really no like the best IDE for C.
All true. Yeah, and why there's no ID for C is another interesting conversation, but we don't have time for right now. But yeah, I worked with James for a number of years, and I know why Java is a better language for tooling than C. You probably can figure that out if you haven't already. So, but we have another collaboration going on within Oracle with our NetBeans division, and there's a version of NetBeans now that connects to programs running in Truffle, because you can't use ordinary debugging technology on Truffle programs, so our API allows NetBeans, so you can actually debug Truffle programs. Anything implemented in Truffle, you can debug with NetBeans now. It's on an experimental branch. It's a collaboration. It's ongoing, but we're actually thinking that NetBeans is going to become the full-service IDE for anything implemented in Truffle, including this multiple language stuff. So we'll see a little bit more about that. So now I want to show you 3 demos. We did okay on time.
Mm-hmm.
I'm going to show you something about NetBeans, which I just mentioned. And then I'm going to show you my command line client, which I just found a new bug in this morning. It's always reliable. And then the work at King's College that's only just now started up, that I'm sort of supervising at the moment. But they're really interested in editing, and they're really interested in editing the problem of if you're combining languages, traditional editors. So if you're doing multiple language stuff, but you want to work with a normal file system and a normal editor, you still have to have every language in a different file. So we're looking at ways to kind of complete that. So let's look at NetBeans. Here is NetBeans poised in some Java code. If you can read that basically there's 3 little static variables that have snippets of code in 3 different languages. SL is our demonstration language, SL for short, Ruby and JavaScript. Okay, so those are tiny, tiny little program code, pieces of code. But we're in Java now, and the Java code has looked for a globally exported symbol, I believe, and is about ready to invoke that symbol. So this is now a cross-language method call, if you will. So you step in there, and you find yourself in a piece of JavaScript code. This is not new so far. NetBeans has been able to step into JavaScript before, but only when running on the Nashorn implementation of JavaScript, which is the one that ships with the JDK. This now works with the Truffle implementation of JavaScript. And you can see that there's some Java code, or some JavaScript that imports these 2 external symbols to implement factorial. And so we're going to do this the hard way. So the line that we're stopped at is going to do a decrement operation implemented in simple language. So we'll step into that. So if you look, you'll see, you can kind of, I'll see what's on the stack and see what's in the frame there, what's going on. So we'll step into, again, and now you're in this simple language, which I could say it was a toy language, but it works, okay? And so here we are, decrementing this variable. And again, you'll see there's some simple now, then there's some JavaScript, and then there's some Java. So we've got a multiple language stack going here. And then you step back out, and there we are on the next line. We're about ready to do the next thing. We're going to do a multiplication operator between 2 numbers, so let's do it the hard way. We're going to do that in Ruby. I don't know why. And we're going to step in, and now we're in a piece of Ruby code. It has a different syntax. The export operation looks different because you identify methods differently in Ruby. This doesn't look the same, but it still goes back to this global symbol. And so again, this is kind of just a snippet of what it might look like in a multiple language world that we can support fairly seamlessly. And the interoperation work they've done is pretty interesting. It's not a general solution to all languages for all things, but there's a lot of situations where you really do want to pass some basic information from one language to another to take advantage of stuff that it can do. So for example, we have an R implementation. There's things R can do that's really hard in other languages, for example. So that's a good example where it's much more easy to see use cases where that really matters. And you need tools. How many of you have ever worked on a mixed language environment? I feel your pain. Usually there's no debugger that will do both of them at once, right?
You step through the interpreter with GDB.
Been there, done that. Yeah. When I was here, our system was basically implemented in Franz version of Common Lisp with C for all the GUI rendering.
You can switch perspective on the same workspace, and then you change the runtime domain.
Okay.
So that you use different debugger in different.
You have to use different debugger.
Yeah.
So again, all tools all the time. It's a productivity question, so that's why we're trying to focus and leverage this stuff here. So that is the NetBeans demo. Just for grins, I'll show you, see if I can make my command line debugger work without too much awfulness. Does that look legible? Big enough? Okay. If you want me to make it bigger, I have a problem with that. But okay, so let's see. This is actually a subset of the previous demo. So we're in JavaScript. So let's see. So this actually, it has a respectable command set. It actually is a debugger. It will do stuff. And we said, let's see what languages. So what languages? So there's 3 languages. Where'd they come from? Well, we now have a platform API for registering languages and you basically put a language implementation on your class path. And if you put it on your class path, the debugger will find it, and you have a fully truffleized interoperability language available. Okay, and the current language is JavaScript. Okay, so I can change that. So, but I'm in JavaScript. If I can just say eval 7, and this is just a top level evaluation, right? I mean, there's no programs running yet, but I can just, it's kind of like a REPL, and I can change to simple. But if I try and do that, it doesn't work. The reason it doesn't work is that the simple is an example of a language that doesn't naturally have an eval in it. You can't parse a fragment, so that doesn't help. So let's load some code. And let's see. Let's load. So you should recognize this name. This is the simple language decrementer. Okay, and then let's load a version of the factorial. Okay, and there we are. And so now we're at the top level, and just like in the Java, we look for an exported symbol, except I think it's broken right now. In fact, I know it's broken. If I try and call that symbol, it'll break. But I should be able to do this. It used to work. Okay, so that is a debugger call that says, here's a global symbol, here's some arguments, actually run it, as if it were an interoperating call. I know it breaks, so I'm not even going to bother to try and run it. The debugger won't break, it just throws an exception that the debugger says. But I can also do an eval. Since I'm in JavaScript also, I'm in the environment, so I'm actually in the language environment of what's on the top of the stack, which is JavaScript. Wherever you stop, there's a language context for the halted program, and it says right there that that's JavaScript, so I know what language is listening right now. It's JavaScript. So I can still, as before, I can say, eval 8, but I can also say, oh, that's broken too. Okay. Oh no, because they haven't run yet. Okay, so what I can do though, eval. Okay, so that's a legitimate JavaScript thing. It's been defined, and so if I run that, it's just going to work. Okay, so I'm in JavaScript. But I can also step into, so I can say eval s. This is the standard debugging thing. And by I say s, that means I want to step into and halt at the first statement. Well, the first statement, as it turns out, is my ff5 call. Curious. So if I say, what's on my stack? Well, I'm in this program called ff5. Okay. And I need to step twice to get out of it. It's a bug. Okay, and now I've actually stepped into this function. So if I do let's see, here I am. Okay, so I'm in two different places. And this is, now I'm just an ordinary debugger. I can sort of say step. I can say next and whatever. Okay, but here I'm poised now to make that same cross-language call. Now if I say eval, and you'll see that I'm in this actual language context. If I say step into, and sure enough, there I am in simple. You can see where I'm in the backtrace. You'll see there's a separate frame, stack frame in there that's at the interoperation call. Not particularly usefully displayed at the moment. But again, it's a multi-language stack. And I can say, well, what's this frame look like? See, the commands are all pretty much language agnostic, right? This is a frame in JavaScript. This is a frame in simple. I just can't eval here. If I step back out again, here I am. And I can say, well, what's the frame here? And you can see, again, just basically a debugger. Just does this. The only difference is it's sort of language agnostic in almost every case. There's very, very, very few things here that are language specific so far. So that's an example of a client of the debugging code, second client, if you will. And for the third client, okay, I'm going to show you a video of what our collaborators at King's College have most recently done. They've only been doing this for a couple of months. I'm going to have to turn the audio up really loud.
There might be an audio plug somewhere in there.
Okay, great.
I don't know if it'll work then.
It's an
It's-
HDMI.
Oh, yeah.
Oh, perfect. Okay. Is this showing up okay?
There's another one over on.
If you
on
would,
us.
I've had good success with just running off the editing bar, that means disconnecting.
Yeah.
And there's this audio control, there's the up and down button, and then the
Well, it
volume.
could be.
Just forget it.
I'm
Okay.
not sure if you're
You're gonna have to
Yeah,
just,
let's-
we'll just go.
That's with it.
We'll hear it, I'm sure. If you just turn off that thing.
I'll point in your direction so you can hear it.
Eco is a unique editor developed by the software development team at King's College London. It has the look and feel of an ordinary text editor, but has the ability to parse multiple languages with the power of a syntax-directed editor. It allows us to write and view polyglot or composed programs with ease, as we'll soon see. This program is written in Oracle's simple language, a cut-down version of JavaScript. The blue overlay here shows a new feature of Eco that we are working on, the automatic visualization of runtime behavior of polyglot code. The blue highlights show the results of the truffle code coverage tool. The darker the heat map, the more times the line of code will be executed at runtime. To see more detailed information from the profiler, the programmer can hover over the text here to see textual information on tooltips. Profiler information here is stored with the AST nodes, so if we change some of the code, we can redraw the heat map automatically to show the new changes. This file contains polyglot code. The code with the white background is written in JRuby, and the code with the pink background is in simple language. Truffle has support for running these polyglot programs, and Eco allows us to view and edit polyglot code in a single file. Eco also enables us to visualize cross-language profiling in exactly the same way that we were able to examine the simple language example earlier. As with the previous example, the heat map here is drawn by the code coverage plugin from Truffle. The simple language function clamp has been called by the Ruby code at the end of the file 10 times, so the number of paths through clamp that the profiler has taken will add up to 10. This is easier to see if we turn off the visualization of the language boxes, which denote the boundaries between the JRuby and simple language code. As with the previous example, the heat map is drawn live, so if we change the code we were editing, we can rerun the profiler to refresh the information we're seeing. As we have seen in this demo, Eco allows users to do two unique things. Firstly, we can write and run polyglot programs in a single text view. And secondly, Eco can easily visualize cross-language program analyses. Thank you for watching.
So 3 different clients of the instrumentation framework and debugging API. And we're pretty optimistic. This is a 1-year collaboration that we're only 2 months into, so I'm really looking forward to seeing what they come up with.
How much demand is there for multiple languages in one file?
Well, if you're going to deal with true multi-language systems, it would be a productivity improvement not to have them separate. File is a lousy abstraction for programming anyway.
Sure, but I mean, like,
And
presumably your files shouldn't be that big to begin with. You probably want them, I don't know, a few hundred lines top,
good question. Yeah. Part
right?
of that's
Like,
language dependent, of course.
One example that's maybe a little bit different, but we have Oracle here, so SQL is always jammed in, right, in a string.
right.
So if that were
Yeah,
part of the
so
language,
yeah,
that
people
would
who
be
program for Oracle program in PL SQL, which is PL SQL is an Ada clone that allows you to embed SQL queries. And then you can actually embed code fragments into SQL in some situations as well. And as we are pioneering a trajectory that we hope will let us run some of these dynamic languages, Ruby, R, JavaScript, in the database safely and quickly and fast. We think this is an opportunity. But again, this is obviously kind of research. That's one of the reasons it's being done by a university collaborator, because it's kind of one of those slightly over the horizon things, and therefore properly done by a university research group. And they've been doing multiple language work for years. They actually have some very interesting history behind them in this area. So having them poured onto our system creates some opportunities for stuff that we can try. So even though in a sense we're looking towards niches that are understood at Oracle, part of our job is to create opportunities for things they haven't thought about yet. Yeah?
Do you have to run the problem at least once to figure out the coverage? For example, how many times to loop run?
Well, yeah, I mean, that's I think I understand your question. It's a dynamic tool, so yeah, you run it and it counts.
So in the background, the tool actually runs the whole problem.
Yes, oh yeah, she would pull down the menu that would say run, and it would rerun the code and then refresh the numbers, yeah. So she was explicitly running it.
What if the program takes in like a parameter so that it changes the
Yeah, well, you'd have to write a call method somewhere in the file and then say run this line or something. Eval this line, and then it would do the same thing. But yeah, she was sort of manually changing the constants, right?
Yeah.
But it would be the same idea.
So the profile is for certain input.
Yes, exactly. And one can imagine a lot of audit. I mean, this is a two-month prototype, right? This is really just a proof of concept that they can get in runtime data back out of Truffle and into their editor. One can imagine a framework, a whole like IDE framework that just has this stuff built in, right? It would be pretty interesting to be able to sort of get some approximate performance feedback on your changes sort of step by step. Would be kind of cool, right?
Another question that since this is a modified version of JavaScript on Truffle, so how do you guys manage to sync with the mainstream JavaScript updates?
Well, actually, I don't think of it as modified. They're actually ahead of some other groups on ECMA 6, right?
Ours is the only fully compliant ECMA 6 implementation that we know of.
Yeah, we are ahead of the curve. Yeah. So those are the slow-moving guys that have a problem.
All right. Hope it's not the mainstream.
Yeah, okay, so I mentioned these guys. So here's my finale. So for those of you who decided that you have a career ahead of you building virtual machines, I'm putting it straight to you. Here's what I want. No language implementation is complete without tools for programmers. Remember, programmers, tools, and people. No language implementation team is complete without tool builders, even if you have one random person, such as myself, to sort of stand up and make the argument, okay, and gather the data and help create the use cases. You should not let people who are in charge of running programs fast think about what users want to do. It's established scientific fact that people who write compilers cannot think about programs the same way our users do. It's just been trained out of them. It's just a fact of life. And I cited a book in one of my earlier slides where I said, no, it's really not right. Programs are not like that. There's a whole book about the cognitive issues around programming and how people think about code. And the one way in which people do not think about code is as abstract syntax trees. And no platform is complete without tooling support. And that's us, so go. A few brief acknowledgments, a subset of Mario's, basically all you tool builders, however. And so let me thank you for listening. Some of these papers here I listed, you've already seen, I think maybe one you haven't seen yet. That's the François Detienne's book on software design, cognitive aspects. It's an old book, but it's the best we have. And ask me about summer internships. We have such a thing, and there's my email. So, any questions or discussion before we hand back over to Mario? Peter?
Patrick.
Oh, Patrick. Patrick, I've been calling you Peter. Oh my God.
So, optimizing away the checks that you've shown, I've noticed that you still have this reliance that the checks execute in the same order in the optimized program as they would in an unoptimized program. So, if you were doing like loop reversal type optimizations, how does that fit in?
That's a great question. I don't have a good answer for you. Yeah.
So let me understand the question a bit more. Maybe I can give you an answer. What's this? Give me an example scenario.
Okay, so like if you write two nested loops to do, let's say, matrix multiply.
Yes.
If you assume that you can't observe the intermediate state of the program, then anything that calculates the same result is the same.
Right.
And fancy compilers often
Right.
switch the orders,
Right.
right?
Right.
To get strive on access. which means that while it's running, if you click break here, well, now you're in the middle of an execution stream that doesn't actually have a analogous.
No, what our system would do is it would de-optimize, and the system would look as if it was always executing the loops the way you wrote them.
Right, but the state would be wrong then.
Yeah, like there is no equivalent state.
So it depends on where the save points are inserted. If there's a save point on the inner loop, then it's on the inner loop and it can't. The save point has to be able to recover to a canonical state as if you were interpreting.
Okay.
And
And
any,
you
and
end
any
up-
loop optimization, any optimization which invalidates that is an incorrect optimization.
Okay.
If you don't want to observe the insides of the loop, then you don't put the save point in, and then you can't observe it.
Well, this is the problem I often have with like turning debugging on, is that the bug doesn't show up until 10 minutes later. And so turning debugging on means I have to wait half an hour until I actually can see where the bug failed. So removing optimizations should only happen in the small section that I need it. Everywhere else it should be as fully optimized as possible. And I haven't seen a very good tool that did this.
Okay.
Something to look at.
Okay,
Let's
let's take a 10-minute break. And,
Yeah, okay. And just in case you're curious.
okay. Okay.
Okay.
And
Very much. Oh, I think Patrick, I apologize.
and we have some treats from the Oracle cafeteria, which is mostly garbage collection. There are a couple of other minor things worth mentioning. As I said in the original memory management material, it's not just reclamation, it's allocation and all of the other and the barrier stuff as well. So we'll talk a little bit about those things too. First about stacks. So if you have multi-threading, you need multiple stacks. Multiple stacks gives you the opportunity for fragmentation, because how big do you make your stack? It's easy in the world where your data grows in one direction and the stack goes down, and you run out of memory when they meet, but when you've got multiple ones, you have to do something different. So the crew solution is to use virtual memory tricks. Pre-allocate a bunch of address space for stacks, but don't populate the address space with actual memory. And every modern OS lets you do that. And that's what most implementations do. It's crude but effective. Address space, especially on 64-bit machines, is plentiful. 32-bit machines, maybe not so much. And that's what they do. Back in the olden days, people used to do much more complicated stack management regimes when memory was tighter, or maybe they didn't have virtual memory. And they did things like spaghetti stacks. There's also something called a cactus stack, where your stack is, discrete segments, and you have to deal, when you return out of one, with sort of making sure the frame and the stack pointer land at the top of the one below it. But it's possible. There's a little bit of extra code generation and some trampoline codes, and it's possible. And that gives you then the ability to have a piece of stack in any chunk of memory that happens to be phrased. The stacks don't have to be contiguous, and they can grow and shrink. And they don't end up, you don't die when one thread's stack is exhausted. Memory has to be exhausted to die. And I find it surprising that this solution is still used almost everywhere, and that, I look at, say, the JVM and the fact that you have to specify the thread stack size on the command line. That's just like a bug. Why do I have to do that? Why do I have to know what the stack size is? I got this memory, just use it. Well, that's what the current VMs do. And there doesn't seem to be any strong motivation to fix it. The other thing worth saying a little bit about is allocation. We've got multiple threads allocating. They're all allocating in the same heap. We don't want to take a lock on the heap every time we do an allocation, because that'll just serialize everybody. It's really, really bad. And there's a simple technique, which I'm sure everyone could invent in 30 seconds of thought, which is thread local allocation buffers. Basically, what you do is you take the lock to allocate a big object, 100 kilobytes, and then you allocate little objects out of the big object. And because it's thread local, you don't need a lock for the internal allocations. You do get the same issues of resource allocation. How big should that guy be? The bigger you can make it, then the more internal allocations you can do without locking before you have to get a lock again. But more space you waste, and if you have a big server application with hundreds or thousands or many thousands of threads, allocating a big chunk for all those threads that are sitting there doing nothing, just waiting for an incoming request, is fairly wasteful. So the elaboration here gets into adaptive schemes that detect when a thread's beginning to get aggressive about allocating space and giving it ever bigger. So typically, if you use up your TLab within a certain time, the next one you make twice as big, and the next one twice as big as that, and so on. And then you shrink them back, stuff like that. It gets kind of messy, but it's doable. This is the way Hotspot does it. The unfortunate part of that, of course, is that you can only have as much contention as you have hardware threads, but you have a lot more software threads than you have hardware threads, yes.
Can we have an atomic memory operation that would take this for, just allocate the, not have the lock on the heap, just allocate that amount of memory. And then when you run out, then you have the lock, and then you have to free it up. But up until that point, you should be fine. You don't need to have a dedicated buffer space for each thread. Right? I can do whatever my heap pointer is, I atomically add the amount I need. And then I check to see if I've overflown. If I've done that, I lock it out and then go. It's under the assumption that I run out of heap rarely.
You have to also deal with, and I'm not saying that this is not addressable with what you said, but you also have to deal with the fact that in that interval, the thing is in an uninitialized state.
Right.
And so anyone else who peeks in there has to not see.
Right, but when you increment the heap pointer, they can't peek downwards, right? So you've already you pre-allocate, then you start setting up all of your stuff, but you do the pre-allocation first, and then you do all the initialization.
And you're using what, a CAS to?
Yeah, something like a CAS, yeah.
Yeah, might work.
That way
I
you
have to
don't
think
have
about it more.
There is sort of some cost to that, though, right? I mean, CAS is locking.
CAS is
Very
still
cheap.
Right, but that maps to a
not
very
sure
nice
marijuana
low
because-
overhead thing, right? So and you
Well, there's still a lot of coherence traffic you have to deal with.
that's actually low overhead.
Risk 5 is a full fence.
Depends on how you.
Yes, it's not also. That's right, allocation much very fast.
So yeah,
Unless-
I mean,
unless
the
you want
TLab is, effectively doing that for the big chunk, and then because it's thread local, you don't need the locking the atomic table. So I was going to say, it seems to make sense to do this, have one of these per processor and not one per thread, but unfortunately the general purpose OSs don't give you all the scheduler information to really exploit that idea. So if you do your own OS, then you can make that work. But general purpose OSs, it doesn't seem to be profitable to try and make that work. There have been tricks where people have run with exactly the same number of native threads as hardware threads and then multiplex the language threads onto those threads in an attempt to exploit this, but no one really seems to have pulled it off completely successfully. Okay, so let's talk about garbage collection. We'll start with some terminology. So this is the picture that we've kind of been operating under so far, which is a single thread where we alternate between mutation and collection. The easy extension is to go to this kind of a picture with multiple mutator threads and a single collection thread, and a barrier that says when we decide to collect, we have to suspend all the mutators, we do our collection, and then we'll resume them all. But what you'd really like to get to is something like this, where you're doing all of the collection in parallel when you decide to collect. Now, of course, this is the picture you find in the books, and that's not the reality, right? The reality is this, which is one of these guys decides it's time to collect, the others all have to be brought to a halt, then all these guys have to be restarted, and in the interim, nothing useful is happening in these gaps. And the same every time you do a switch in this kind of a scheme. So this is known as parallel collection. The terminology here I find is bizarre. So parallel means the collectors are running in parallel but not at the same time as a mutator. And concurrent means the collector and mutator is running at the same time. Seems like kind of arbitrary. They could have picked that either way around and it would have, the previous meanings of those words would not have affected the outcome. But that's the way the literature is settled, and so I tell you this just so that you know what when you see the words, you'll know what they mean. So, so how do we get there? Well, first let's do a little bit of revision, because there's some terminology that makes this all a lot simpler to think about. I mentioned the tricolor abstraction way back in the GC slides, and this is the same material from there. So the idea is every node in our graph, every object in the heap, is one of three colors. White means it might be dead or alive, we haven't done anything with it, we still have to visit it. Grey means we've decided it's alive, but we haven't yet processed it to figure out what it refers to and color its nodes. And black means we're done with it and we don't want to go back to it. And we want to progress from white to grey to black, or white to black, and we don't go backwards, generally speaking. We'll get to some exceptions to that later. And just to make it concrete, you can watch the movie again. So as we colour out from the roots, we colour things grey. As we process them, we make them black. So we've dealt with B and C, they're now black. We scan E, which means colouring the things it refers to. And then we colour that black, and so on and so forth. Fairly straightforward. Now, well, we'll get to the concurrent world in a minute. Let's deal with parallel collection first. So in a parallel collector, the correctness problem is not so difficult, because the mutator and the parallel collector are not really concurrently, right? If they are, that's a bug. That's the first bug you have to fix if the two are overlapping, because they're not meant to overlap. The challenges are all in efficiency. So what you've got to do is be able to suspend all the mutators and then restart them in a timely way, and do the same with the collectors. And that's the tricky part, making that scale well, so that you can do that for large numbers of threads, particularly on a big system. And I refer you back to Cliff Click's points about this, and in particular the scheme that they used, which was to always make sure that when you suspend a thread, it's suspended at a safe point, so you don't have to resume it just to get it to a safe point, so that you can actually do the skid stack or stack scanning. And that's easiest done with hardware support or a scheduler support. Yes?
You made the previous point that you can launch as many threads as you have processors and have language system multiplex over them.
Yes.
Would that be much simpler?
Yeah, that helps with this, because then your scheduler, if you write the scheduler, you can make this work.
Right.
But
So-
if you're relying on stock OS and stock preemption, then you get into this problem that stuff gets preempted at arbitrary boundaries, and before you GC a thread, you have to be able to advance it to where it's safe to GC it, which means taking it to a GC safe point, or doing something even more devilish like tracking, being able to abstractly interpret up to that point from the last GC point or something like that.
So what advantage is there to using the OS threads directly?
They're there. They're there, and they're on everybody's machine. So when you build a language implementation, it's not a strong selling point to say, oh, and by the way, you need our custom OS to run this language.
Well, like Ruby, for example, has its own scheduler essentially. It's like green-threaded across one processor.
Yeah, but that's really a single-threaded implementation, isn't it?
Right.
Yeah. So there you get no concurrency advantages.
Yeah, but if you were designing a concurrent system, I feel like I would launch as many threads as I have processors,
Yes.
and green-thread over those.
It's been done. It just wasn't very successful. It's hard because you're going against the grain on everything.
Okay.
The underlying system is trying to preempt you,
I see.
and you're trying to not be preempted or to manage the preemption. Okay, so suspending and restarting. You've got Amdahl's law to deal with. If there's anything serial in your collector, then parallelizing it isn't going to help. And you've got to spread the load evenly, because you're walking a graph during a collection. You don't know what the shape of the graph is. You don't know how far you're going to go down it from any particular starting point. So you have to probably do something like work stealing to balance. What you can do, however, is to have just the same number of parallel collector threads as there are cores, because and not use the same threads for collection as you're using for mutation. So you bring all the mutators to a stop, you start with the parallel collection threads, and those are evenly balanced, at least in thread counts, and then resume all the mutators when you're done. So that's a trick that does work and is quite effective. So the general paradigm in a parallel collector is each thread is running a loop that looks something like this. Is there something left to do? Then I'm going to figure out what I'm going to do next. I'm going to do it, and as a side effect, I'm going to generate some more work to be done and put that into the pool for either me or one of the other threads to do. We keep doing this until there is no work to do, and there has to be some kind of termination condition that will get us to that point.
So do the first two steps require some sort of a coordination or locking, pulling work out and?
So it depends exactly. We'll look at an example or two. So an example of this is parallel marking. Okay, so the work list here is the set of grey objects, because that's the frontier of where you've got to go after all of the things you've visited and you don't want to visit again, and the white things you haven't got there yet, so you don't know there. So the set of things that you're working on is the set of grey objects. And so the acquire phase is take one, at least, grey object from the work list, atomically. So there you have to have some kind of coordination. And say, I'm going to work on this, you don't get to work on this, I'm going to deal with this. To actually deal with it, you've traced its reference and shade them the appropriate colour and stick them on the list. So that's also generating work and doing work are combined. And then once you're done, that thing's done and you move on to picking up the next one. So, and we're done when the set is empty. Now, if you do this literally on one object at a time, then you're going to contend for the lock on the set hugely, right? So you probably want to grab more than that, or you want to decompose the set into bigger entities which are thread local and then have stealing to pull stuff out of the other guy. So when yours is empty, you look around and go, he's still got a lot to do, I'm going to take some of his stuff. This is not really tied directly to parallel stuff, but it's worth mentioning at this point, which is if you're going to, one of the difficulties here is because you're walking a graph through memory and the pointers can point anywhere. Many of the first loads to an object are going to miss in the caches, and so you can mitigate that partly by doing a prefetch. As soon as you've got the object that you're going to process in your hand, you find some pointers from that thing and you issue prefetches because you know you're going to visit those again soon. Now that only works if you're going to visit them again soon on the same processor. There's no point doing a prefetch here for when the other guy's going to take the thing off the queue. So one solution here would be to pull a bunch of things off the set for you to work on, issue a bunch of prefetches, make sure that all of those things are going to be yours, and then let the other guys work on their own piece. So as I think I just said this, having a single list gives you contention. Per worker lists lead to unbalanced processing because you don't know the shape of the graph. So one starting point might only refer to a single object and the other one might have everything else in the heap. Right? And if you just run those without any work stealing, it's not going to be any faster by parallelizing because you only get one thing done in parallel with another thing. So okay, parallel copying. That's a little harder because parallel marking is generally speaking idempotent. So, but copying is not. So you have to be a little bit more careful about how you do stuff. You don't want to copy things in. You have to install a forwarding pointer, and acquire and install and copy all in a way that makes sure that no one else is going to do that. You won't trip over each other. When you get into copying rather than marking, a common technique is to divide the heap into chunks. I own this chunk and you own that chunk. I have a work list of things to do in this chunk. If I find a pointer into your chunk, I give you the thing to do, and everybody works on their chunk. And also helps with things like uniformity of memory access. If you can make sure the chunks are mapped into your piece of memory attached to your processor, then that helps with the performance there too. Parallel sweeping is kind of an interesting thing because you actually don't have to do it with the mutators off, right? Sweeping only touches the dead objects, and so as soon as you're done identifying the dead objects, you can restart the mutators and they can start running, And the sweeper can run in parallel, running through memory, finding the dead objects and putting them onto the list. It has to deal with, has to make we be able to walk a mutating heap. So scanning the heap might be a little challenging, but if, for example, all your dead things are on a free list, or on lists that are generated as a side effect of marking, then you can process those things separately and add them onto the lists that the mutators are taking from. So these can run in parallel with mutation. And if you do that, however, you need to put some synchronization in the allocator, because if the allocators get ahead of the freer and you run out of memory, you want to wait until the freer is done freeing before you decide that you really have run out of memory. So there's a bit of synchronization needed there. Okay, so parallel collection has been used. There's a parallel generation scavenger and hotspot, which is used in very big installations, big multiprocessor systems, typically in the financial world, where they make most of the memory be the new generation. And it kicks in and it runs in parallel on a whole bunch of cores and scavengers. But otherwise it's a fairly obscure technique. If you look in the literature, you find much more on concurrent collection. So instead of this picture, where stuff is happening in phases, we have this picture, which is, the collector is running in parallel with mutation, kind of in arbitrary periods. In fact, there's a much better categorization of this in the book with finer distinctions, but I don't really have the time to go into that. So the interesting thing with this is that this picture is actually glosses over some of the truth, which is that really, if we zoom in on this, right, and we take our two threads and we get them down to the size that we can see individual instructions, then what's really going on is we have barrier code, even in the mutator, that's doing stuff which has to synchronize with the collector. So it might look grey, but really you've got barriers in there. Read barriers or write barriers around the pointer reads and the pointer writes. And the purpose of those is to make sure that the invariants that the collector needs are maintained by the mutator and that everything is hunky-dory. So the challenges are many-fold. So the collector has to be correct, and correctness is non-trivial now. It's really, really difficult to figure out what's going on because you have a graph that's being mutated under your feet as you're walking, which is challenging in the best of circumstances. It has to be fairly efficient, so it needs to be able to keep up with the mutators. If you're reclaiming, but you're reclaiming so slowly that you run out of memory, that's not useful. It has to have pauses that are as low as possible, because the whole point of having a concurrent collector is to spread the pauses out amongst all the mutators, so there isn't a stop the world pause. You're not holding up any individual thing for very long, and you're not holding up the system at all. And it has to be timely, so it can't leave garbage floating in the heap for long periods of time, because then you need a massive heap to deal with a relatively small set of live objects. And perhaps the most difficult thing is to do this without slowing the mutators down a lot. So those instructions that you have to sprinkle in the mutator code have to be short enough and cheap enough that you're not making the mutators horribly inefficient. If we relax any of these things sort of to its extreme point, then all of the others become almost trivially easy to solve. The difficult problem here is making them all balanced so that you've got a system which has good characteristics. Reasonably good characteristics in all of those, no terrible characteristics, and is good in at least one or more.
Are those fundamental trade-offs?
Sorry?
So the tension, is it just hard to get everything right at once, or is there actually some fundamental trade-off?
There is no known solution for how to get them all good at the same time, in the same algorithm. That's an open problem. And whether it's an insoluble problem,
that's what I'm asking,
or a soluble problem but we're just not smart enough, I'm not smart enough to tell you. Sorry. And no one else has come up with a good argument one way or the other for whether it's, like sort of the equivalent of NP hard or something. It's obviously not a complexity issue. Is there some kind of an engineering obstacle that makes it?
Wasn't this what Azul is doing with their custom hardware though? With the barriers built into the hardware?
You get to a point where you're just pushing the dirt under a different part of the rug. And it looks good, but when you look at where the dirt is, it's somewhere else. So in their system, for example, it looks like there are no pauses, but right after you do a flip, you've invalidated a whole bunch of page mappings, because the GC relies on TLB mappings being different for the GC. You just invalidated a bunch of those, and there's going to be a storm of remapping events. Which, well, a pause is a pause, right? The end user isn't going to look at it and go, well, that's a TLB remapping pause. That doesn't count as a pause. I can live with that. It's still a pause, right? And there's actually extremely scant data. I believe it's because they prohibit publication of metrics on the system. When you buy one, you can't measure it and publish the data. So no one really knows. And if I knew, I couldn't tell you, but I don't actually know because I've never run the hardware. But I look at the paper and I think, oh, that looks like a weakness to me. So, okay, so I said correctness is difficult to establish here. Debugging is a nightmare because, no two runs the same. So actually there's been a bunch of people worked on trying to establish a framework in which that's reproducible, right? So you make a run and you can reproduce the timings and everything, so you can debug it, but in real production systems you can't. And so the nightmare here is, someone gives you a thumb drive with a 50 gigabyte heap dump and says, this crashed. There you go, find out what went wrong. And you don't get to rerun it, and you have to try and figure it out from there. And there are people who do this, for a living.
They're underpaid.
They're underpaid. Yeah, it's really hard. It's really hard. Also, you can't do some of the tricks that I mentioned in the earlier lectures, which are invalid in the presence of a concurrent mutator. So, reversing the pointers through stuff, that's fine in some techniques, but the mutator's going to have to deal with whatever you do, so that takes a whole bunch of techniques off the table. And then the barrier code. The barrier code is really hard to do in a system like this and make lightweight. It's bad enough to get this light enough in a write barrier, but if it's in a read barrier, the frequency is probably 5 times higher than it was in a write barrier. And if you add 10 instructions into a read barrier, the system is going to be really slow. Solving all of those things is non-trivial. One interesting, so this book, my admiration for this book has gone up since having a look through it again this week. Half of this book is about concurrent and parallel GC. And the real contribution, which is kind of unstated, is that they've taken a whole bunch of the literature on concurrent and parallel collection and they've put it in a framework which didn't exist before, which makes it very easy to describe the differences and the variations in the techniques. And that's something that's a really valuable thing that, should have been like a good research paper somewhere, but it's just in the book as far as I know. And it's motivated by this scenario, which is we have this group of objects, black and white. Our garbage collector is walking there are other objects, obviously not on this picture, walking them. And it's trying to color the grey things to black and the white things to grey and then ultimately black. And while it's doing that, we copy the pointer to the white guy in the black guy, and we drop that pointer. And now we have a white pointer in a black object which we're never going to revisit. So if we never revisit that and we never caught that move or the destruction, we're dead, right? This is incorrect. We're going to reclaim the white object and, we're going to get that heap dump in the mail to analyze somewhere down the road. A good research contribution from some years ago analysed the situation and said there's two things that need to happen for this to happen, for this to be a problem. One is that you store a pointer to a white object and to a black object, and all paths from any of the grey objects to that white object get destroyed. Both of those conditions have to be true for this problem to occur. And so there are now a couple of different ways of attacking the problem. One is to adopt what's called the strong tricolour invariant, which is you never put pointers to white objects and black objects. That means when you try and do that pointer store, you have to colour the white object before the pointer store succeeds. And that has to be adopted by anything that's never going to revisit the black object. So a copying collector, once you've copied it, you've put it on the other side of the fence, you're never going to go back to and visit that guy again. You have to adopt this strategy. The alternative is to break the other condition, which is that all white objects pointed to by a black object are grey protected. It's not quite as crisp as the previous slide, which is easy to understand. But that means that path, if you break that path, you have to detect that you've broken the path and do something, either prevent the path from being broken or adjust the colours in the way that's legal. And this is like a weaker condition. It's implied by the earlier one. If you guarantee the earlier one, you guarantee this one. But it's used in some cases to success. And this is a really nice way of classifying all the different approaches, because if you go through the literature, you have, 100 papers, all written by different people in a different style, with very different languages and different approaches, and trying to figure out what the differences are amongst all of these things from the papers, it's just horrible, horrible job. And this has done all that for you, right? It's gone through, they've figured out what all of the different conditions are, they've, made it all neutral relative to the languages and the systems that they were implementing. And just say, okay, this is one that relaxes that condition, or relaxes that condition, and here's how it does it, and here's the various different barriers. So it's a good product. Okay, so one of the ways they do this is that they think about the mutators themselves having a colour. So when you scan the stack of a thread, then you've coloured it in some way. You've either coloured it grey or you've coloured it black, depending on what you've done with the stack scan. The stack can be a frame at a time. I mean, usually you pause the thread when you're scanning it. It's kind of hard to make that work while it's running. But you pause the thread, you scan one or more frames, you colour those frames, maybe you do the whole stack, and then you let the thread resume. And that gives you, whether that colour is black or grey is one of the distinctions in how you classify the algorithms. So a grey frame can refer to objects of any colour, but black frames have to refer to grey frames if you're using to grey objects if you're using the strong invariant. Then the other way of thinking about it is, what's the colour of a newly allocated object? Is it white or grey or black? If it's grey or black, that means then by implication in this GC cycle, that's never going to be reclaimed, right? You're going to have to wait for the start of the next cycle for it to be eligible, for it to be white again, because you don't reclaim grey and black things. So, but black mutators can't allocate white objects in their roots if they're following the strong invariant, right? Whereas a grey mutator can. So that's another axis of division. And then the barrier actions that are performed within a read or write barrier help distinguish. So you've got only a few things that you can do. You can take a white object and you can shade it grey, adding it to the wavefront and shading grey or black. Changing the colour of the object, and then it treats shading of grey or black as a no-op. You could scan a grey object and make it black and thereby advance the wavefront. In some situations, they retreat the wavefront by reverting an object from black to grey, and that helps with the second invariant in some cases. And all the other actions break one of those invariants. So it's kind of a combination of these things. So what combination is it, and how are they composed? One of the classes of solution is called snapshot at the beginning, which logically speaking takes a snapshot of the heap as it stands at one moment in time. And the collector only considers that version of the world because that already has some garbage in it. The objects in it may change, but if you look at the graph as it was at that point, then you can reclaim the garbage that existed at that time. So logically, it's a snapshot. Physically, you can actually implement this using virtual memory tricks as a snapshot, but there are also tricks that maintain the logical view, but not the physical view. And then the write barrier protects against the deletion of, so when you're mutating objects in the live copy, you make sure that you don't violate the weak invariant by deleting pointers to things that might get snuck away. And because it's a snapshot, we're basically taking all of the threads, coloring them black at the beginning. Another class of techniques has the mutators being grey, and they use the strong invariant and the write barrier to prevent storing white pointers into black objects, but you don't need a read barrier in those cases. And an example, there are lots in the book. I'll pick this one because it should be very close to what you're familiar with. Baker's algorithm is you're copying garbage collector with a little bit of a tweak. So in the Baker's algorithm, what we do is at the beginning of collection, the heap in from space is white. We scan the stack, and everything that we find referred to from the stack, we copy to 2 space and we color it grey by putting it in 2 space, and then our mutator is effectively black. That's exactly the same as what you've implemented, I believe. The trick is, though, that we then resume the mutator. Right? Having done that, the mutator is now running. And to make sure that everything works correctly, the mutator has a read barrier, so that any time it tries to read a white pointer, the read barrier traps, the object referred to is copied into 2 space, and it gets a pointer back to the new copy in 2 space. So it never sees anything in from space anymore. The mutator only sees stuff in 2 space. If it tries to access anything in from space to see a pointer, it gets mutated. So in effect, the mutator is driving the copying for you. Everything it sees that hasn't already been copied gets copied. And in parallel with that, or interleaved with it, you have your normal copying garbage collection process, which can be incremental now. The minimum increment is 1 object. Finds a thing, copies it. Resumes the mutator. Finds a thing, copies it, etc. That's a nice serial implementation. The original version of this was a serial implementation, and it was one of the first incremental algorithms, because the pause time was bounded by the time to copy 1 object. And then eventually, the combination of the mutator and the collector drive all of the white objects into the grey area. You process all the grey things, they all become black, and you're done. You flip, and you go back. And it's actually, well, the only thing you have to do from your code to make this is really put a read barrier in, and you'd have a working incremental collector. So I present that one only because it's close to what you're familiar with. The book has many others, and they're from difficult to mind-bending. I mean, they're really very, very challenging algorithms to understand, especially if you start from the original descriptions. The book has done a very nice job of distilling out the differences and saying, well, it uses this thing in the right barrier, and it's a grey mutator with white new objects, and kind of that's all you need to know. So it's really, really nice. You can go through it and try and match the algorithm to your requirements. All of them, however, have weaknesses in some case or another. Sometimes the weaknesses are very hard to figure out, but they all have weaknesses, because otherwise one of them would dominate now, and they don't. And there's a lot of material in the book. I haven't had time to talk about concurrent reference counting, which is another chapter in the book. I actually don't know anyone who does that. And real-time GC, which I just don't understand at all. So, which is the last chapter of the book, and just seems like an oxymoron to me, but I still have to figure out what they mean by that. The final thing I'll mention is something that isn't in the book, which is layering of collectors, right? You can build a system using a whole bunch of different GC techniques just by layering them one on top of the other and having barriers maintain sets of pointers from one space. And so you partition the heap. A barrier says, okay, this guy's pointers to that space are the roots for that space's collection. And it's fairly straightforward to do this, actually. It's not very difficult. So you can think of generation scavenging as a layering of copying collector over a mark sweep collector. Hotspot does parallel scavenging for the young generation, and a variety of concurrent techniques for the old generation. And I've worked on a system that used marking, copying, and reference counting. Reference counting is attractive in bulk storage because pointers on disk don't change. So the reference counts don't update except from memory, and you can store deltas that update to the pointer in memory so that when you bring it back in, you can combine that with its original reference count and reclaim it. It's an interesting technique for bulk storage. Okay, that's the end of the GC section. Any questions on that before we go to the composition?
So just a general question on concurrent GCs. What kind of performance overhead do they have, like on the total runtime of maybe? So for example, if you have a server process which is not really interactive,
it's a pretty substantial penalty depending on how small you want the pauses to be. So tens of % is not unusual, even with occasional long pauses. If you want no occasional long pauses, you're pause intolerant. 2x, 3x, kind of in that range. 5x, depending on how well engineered it is. The last, percentile of long pauses is very, very hard to eliminate without losing a lot of efficiency. That seems to be where the practice is right now. If you look at something like Hotspot, it has this G1 collector, which is concurrent in the old space. And that's probably 20 or 30% slower than if you said, I'm running a batch program, I have no user interaction, I don't care what the pauses are, I'll use mock sweep or something like that in the old space. Because the barrier, it's like 10 instructions. It's not trivial. It's not trivial. Okay. Petition time. You're on.
So we have 5 applicant teams, and
Anyone bring a drum?
snare, yeah. Okay, so I just have a bunch of measured times. So I took all of your benchmarks. The score was you get whoever runs fastest gets 100 points for that benchmark. Everyone else gets the percentage of whatever they achieve according to the fastest one. So this is benchmark 1. Who was benchmark 1 again? Sorry. That was you?
Yeah.
Okay. Right. Do you want to explain what the benchmark is supposed to do?
This was actually just a simple rewrite of pseudoku 2, which used boxed integers instead of integers. So every
So boxed at the Feeney level.
box at the Feeney level, yeah. So it's a class. You have the value inside an object, and it's actually like I think 2 or 3 levels of hierarchy. And that's about it. That was the only change.
What optimization were you proud of for that?
Well, yeah. So I guess the main one for this was the fact that a lot of the operations were on getting and setting slots of that were defined in a type that was higher up from the type of the actual object, as well as method calls.
Okay.
So that's not something that's really trivial to do with Feeney's prototype system.
Right.
So what we did was we had so in our VM types represent the entire chain, which means that if you create a new object of type T1 and that inherits from an object of type T2, then now this object is of a type T3, which essentially represents the combination of T2 gives T1. So every type has a fully defined chain. So if you have a method call on type T3 now, you can cache that. Same with slot accesses.
So the tab itself has the entire hierarchy.
Yes.
Does the object itself still have a link in it to go to the parent?
Yes, the object has a link to go to the parent.
Okay.
But you probably don't know the type. You
So
probably don't.
when you read an inherited slot,
Yes.
what do you have to do to get to that thing? Do you have to follow the link? And
Yeah,
do
you
the
still have
lookup?
to follow the link because it's a product. So
Right.
if you set a slot of an object which belongs to its parent, and then you access from the parent pointer, you still need to have this.
Yes.
So for correctness, you do that. So what we do when we're getting and setting slots is we also cache the depth.
Right.
So we've got
Okay.
if it's of this type,
Okay.
then
It's
this is
3
slot
up.
index 3 at the depth of 2, so it goes
Okay.
up.
Okay.
Yeah.
All right.
Mario, did you do actual parent inlining for truffle?
I'll tell you.
Okay.
The reveal's coming.
Actually, I just thought of another idea for that.
Yeah.
I think of like creating just first emitting a bunch of get parent instructions in like just a serial, and after that it gets slot, and then at the call side you just jump to the corresponding slot of that emitted code.
So you skip the.
But I didn't do that. I just thought that
Can you say that again?
like do you mind if you understand?
Okay, so you don't want to run this loop.
Right.
That's annoying.
Yeah.
So what you can do is you can generate a bunch of follow parent, follow parent, follow parent, follow parent.
Oh, okay.
Just like
And then
define a
actually do that
jump to the-
generically, like outside of their maybe at the end of the code,
Yeah.
and then
Oh, okay.
That's pretty clever. That's
So there's another reason we actually have the benchmark, but that optimization was never implemented.
okay.
So when you use boxed integers, for example, and pseudocode to create struggles, like billions of them, it causes GC to be invoked many times.
Yes.
But the fact is that boxed integers are immutable. They have a slot which is never modified once the object is allocated. So if it was possible to just to detect immutable objects and then not create many copies of them, we would just have, for example, in pseudocode, just 10 instances.
I see.
But that seemed too hard to implement. I mean, it's not too hard to implement, but I mean, it seemed like the analysis to figure that out would not really give you
I
that
think
boxing.
there's some other languages that would be better fit. Fini doesn't have a definition for immutable slots, right?
Yeah,
so it's
right.
very hard to know whether
Yeah, they're immutable if you can't find a writer.
yeah.
Well,
Or,
yeah,
or
I mean,
if there's no right in a path
Yeah.
that's executed.
So there's no set slot with that slot name,
Right.
and you can't dynamically create slot names.
Keep on to that. Keep on, like, hold on to that thought, because there are languages that have a definition of like immutable slot.
Yeah, sure.
And that is very
But
obvious.
yeah,
Okay.
Who's benchmark 2? Well, maybe I.
So
rename it.
higher's better,
So
right?
higher's better.
Higher's better.
Okay.
Higher, this is points, 100 points at the top. Yeah. I should have renamed all these benchmarks.
Sure, the source code. Yeah.
benchmark
I have
two
a
was
source.
linear
Yeah,
regression.
I have benchmark too.
Linear regression was
Yeah, that's our.
Oh, that was ours.
It's
It was
our.
very
Wait,
similar.
yeah, they can tell us.
Yeah.
So we try to do like boxed integers as well.
But
Okay.
4 layers deep.
Yeah, 4 layers too.
Because so our original plan was actually to have basically do exactly what he did, except limit the amount of layers we go down, and then just kind of.
The reason for 4 is because an int is like we assume there's at most 256 classes, so that you can use 8 bits to represent a class name. So you can like do a hash function, which you put them in one int, and this guarantees there's no clashing. But I mean we don't have time yet, so and actually I tried. It's actually
How do you detect overflow?
So we just kind of assumed overflow was undefined.
Oh.
We kind of assumed that.
Oh.
yeah, we assume you are not going to find more than 256 classes.
But the thing
benchmark
is we didn't even get around to getting to that.
Okay.
So the thing is, we found a bunch of bugs we were fixing, and also we tried to do top of stack cache because that seemed more relevant.
That was very important, yes.
Yes. So we did that, but debugging that took enough time.
Because every group did top of stack
No,
cache.
right. We didn't.
No, not everyone did help with that.
Okay.
Okay, so there is this general theme where for your inline cache, you want a very quick check to know, even if the method is in the parent, you want to jump to it from this clock.
Right.
And that requires some sort of hash of your hierarchy.
Right.
Yeah.
Right? Okay. Which
So-
you did, James also did. But there's an important part, which is this hash could collide, right?
So
So how do you handle this collision?
Oh no, because ours specifically we were.
we put them into an int, so there's no
The
clash.
You
point
just
of
shift the
it
type
is
and you
that-
add another one?
Yeah, it's exactly. The hash was supposed to be that you basically just do a shift, so you're guaranteed that they won't collide.
Right.
What if there's
Sure.
Fini does not have a finite length on
Okay,
parent length.
Sure.
But you assume there are not more than 253 classes.
Yeah, but
If
you
this
can
is
have one
something-
class which inherits from another
Yeah.
long-chain
We have like
object.
10.
Right, so there's a limit to the depth. And we also assume there's no crazy program for direct inheritance over like, you can do at most 8, right? Because
Right,
it's 60,
but then your program fails.
Yeah,
You
yeah.
can hear it from
Yeah.
yourself,
Yeah.
recursive
Yeah.
inheritance.
But
Yeah.
in the end, we just didn't do it. So it's not even important.
So James does actually have a really elegant solution for detecting overflow in the parent lane. Do you want to talk about that?
Sure. Basically, pick the maximum number of classes you expect. It could be, 3, 2,000, whatever number of bits. Now the trick is that you use the uppermost bit as always high. And so when you shift, you're shifting up that uppermost bit as well. It's always high. So when the most significant bit of your number is high, you know you've overflowed.
Okay.
And after that point, you know the trap. And you assume this behavior is rare. But you always handle the scenario, and you'll never have this issue of, oh, shit, I accidentally overflowed.
So what's the hash function?
The hash function
is a
is a shift,
Yeah.
Okay.
but it's a shift with keeping the most bit high, uppermost bit high.
I see.
And that way you can always check to see if you've overflowed.
So I guess we create new types completely. So if there is more than, if you're overflowing, you just don't.
But you still have to decode it back
Yes,
into
yeah.
the original
Yes.
type.
Okay.
Okay. What was this?
So it's basically like what you talked about. We use a wall loop to create a bunch of chain of
Yeah,
objects.
1,024 link, right? If you notice, this one.
It's 1,024 parents.
Yeah, it's not
Zoom
even
zoom up.
and then it also requires to have a polymorphic inline hash.
Yeah.
So
Yeah.
luckily we didn't do it. If you do it, then these tests.
But actually, I just noticed that our task can be inline and then it will not be polymorphic inline.
So what are the other bars mean? The ones that don't exist, are they?
I think they're just really small.
Yeah, they're really
It's
small.
just-
I think they're just really small.
Yeah.
I said I wasn't going to try to optimize this.
Yeah, there is something special about this graph. If you notice, there are only 4 chains at the bottom.
Yeah.
This one is
It doesn't
passing.
fail.
This one was passing for us, so
Okay, so maybe it wasn't here. So this killed someone.
Well, the initials are there, so is your initials there?
no.
No.
But we did this. We specifically fixed bugs to pass this.
I guess when you ran it, it didn't. Do you do it in OSX or do you do it?
I tried both. I specifically spent time to fix it in Ubuntu.
It could be that in my environment it blew up,
Okay.
which is a dark question.
Well, whatever. It's.
Okay, so this is 1,024 parents, right?
Yeah. Because we didn't use the hashing function, so this one should work.
Actually, we did the transitioning as needed, but we also cache the parent type so that every time we create an object of the type we've seen before, we inline cache and then we just don't have to do the transition for that.
I don't understand by transition.
Sorry, could you explain that again?
Like you said that when you see a parent type, you have to create a new type.
Okay.
Do you do that right? You do when you see an object and then you want to create an object and you see a parent type and create a new type for that.
Yeah, that's it.
So basically, we keep track of the runtime type. That's the type he created, and also the base type of the object. So that the base type means just the object tag we have like for normal mini programs, right? For 5 or 6. It's not runtime created.
Okay.
That's for slot operations, but we just keep track of runtime type. But also that inside the JIT code, we also have an inline cache that detects if there's the type we have seen before, like if we already encountered that code before.
Okay.
Oh, so when you're allocating objects.
Yeah, when we're allocating
Okay.
objects. So do you do transition for
I
every
think
time you create an
so,
object?
but I'm not sure it's correct.
No, yeah. We all have, within the class of every object, there is a transition
Language
to
needs a real
other.
Right, but then you have to look up the table, right?
Yes, there's a table lookup.
Right, so we just ignore that table lookup because we have a if
We're going to get
branch.
thrown out.
Oh, okay,
Exactly.
that's
Thrown out.
And then so that creating objects will be
Yeah.
Get
creating
thrown out.
Right, so the object allocation operation is
We
really
better move it.
Fast
along,
forward.
'cause
Yes,
yes, otherwise I don't
yes,
think I have time to wrap up.
Okay, benchmark 4. This is a long running one. This is your benchmark.
Yeah, this is my
This
benchmark.
one-
So basically, you need dead code elimination. You probably, if you had any GC bugs, you might have got exposed to something in here. Also, since I have register allocation, my GC is faster than everyone else's. Since the loops.
Is this the one that the pi calculation?
Yeah, the pi calculation. Yes.
Okay.
And then lastly, you have to do static analysis to remove the jumps or the tests on the integers. And after that, the only way to beat me would have register allocation.
How long did the whole benchmark run in?
The whole benchmark runs, well, this is actually longer than mine. My system runs at 2.7.
2.7. Okay.
Yeah.
Alright, benchmark 6, I think this was.
I only got 5. Nobody sent me
There
5.
was one that was added.
Yeah, this
Oh,
is
okay.
the-
I've
this
never
is the
seen that.
floating point
All right.
Oh, this is the floating point one, yeah, from Jack and
Yeah, from
Maddie.
us.
Yeah.
Okay.
Honestly, we didn't do tricks, we just wanted to have fun.
Not as bad. Okay.
Okay.
I like the floating point library though. That's
That's really cool.
Okay, and then here's stuff that I wrote. This was a very, very short running program. It's recursive. Memory startup time. Yeah. So
Startup time.
and then Jack, so like you said, yours is pretty simple, right? So you got a really good score on this one actually.
Okay.
And this is important. Chains. This was.
Okay.
Yeah. Okay. This one I actually tried to break people who cache the parent links.
Yes.
Yeah.
Yes.
Because it has different parents.
Yes.
I wrote this one. James, you want to explain this one?
Yes, you'll notice that it never prints, so you can analyze whether it prints and just kill the program immediately.
So this is, killing it is not as simple as like looking to see if there's any printfs, because there are printfs in the program.
Right.
If you do a trace of reachability analysis,
Which
you
I
can
did.
tell that whatever you reach never calls. And then
So that's the problem, that's not fun.
Yes.
It's a reachability analysis. But if you do the reachability analysis, you realize it's not reachable.
But you have to do that.
Do you have the result and remove James to see the rest?
That'd be a good experiment. Okay, this one was fascinating to me actually. So this was big num implementation, Fibonacci on big nums, with a really inefficient big num implementation that allocates tons and tons and tons of objects. Jean-Charles Smooth, do you have
I don't know.
an explanation for why yours is so good?
What is it doing?
Doing Fibonacci with a big num.
I don't know. Maybe just inline.
So,
inline much of the stuff.
Yeah.
Okay.
And he also has a really fast object allocation operation that you mentioned, so lots of allocations would be fast.
And you have your last.
You have fast object allocations, right? So
I mean, that's only for catching.
Yeah.
It's only for.
yeah, but this is all big numbers. So
I'm not sure. Is it
Yeah.
is it doing transition?
Was it-
He's doing a shift, right?
No,
He's doing that shift. So
Okay.
probably it's not.
Okay. Well, for whatever reason, it's very fast. I was really impressed with this one. I didn't think this one was very easy to optimize. I don't think this one is. Yeah. Okay. Another fast running one, Fibonacci. Not the worst. Here's your recursive Hanoi. This is another one that allocates a lot. So we're seeing a pattern that Sumiuka and Genchao is really good at allocating. Yeah. And here's Sudoku, which James optimized the hell out of.
so that is also just print 200.
No. Actually, I considered doing that. In fact, that would have killed benchmark 1 too. I would have done the reachability from printf. But I didn't think anyone would have done that anyways. But that was the next trick to do.
So why does your implementation optimize away complex matrix but not Sudoku?
Because it doesn't print anything.
Oh, okay.
I can analyze it's not printing anything, so just kill it. Now, its clever thing is the reachability to a printf. And then you just follow the trace and you can cut all that. But no, this is actually just running Sudoku 2 200 times.
Cool.
Okay, I think that's it. Cool.
Okay.
Okay.
So, time for the results. Results in 5th place.
Yeah.
Jack and Michael, you get your certificates.
Wow. Certificate
Well
for
done.
place.
Thanks for playing. Thanks for playing. And 4th place. Rowan, well done. Thanks for playing. On 3rd place, Jack and Ben. That's you guys, right?
Third place. Well played. Second place. Zhang. I don't know how to pronounce that. Okay. Second place, close but no cigar.
Wonder who won.
And that leaves James. Your name will live forever. Okay. Well done, everybody who entered. And even if you didn't enter, if you built a working implementation that ran well, the course had its point. That was great. Who looked at this in a loop for me, the speed loop? I got a couple of traces. Okay, what were the instruction counts you got?
I got some 400.
Okay, and 200. Okay, so this program, I wrote this program to show how difficult some things are to implement. So what I did was I implemented this loop with a counter in it. Let's look through what the loop does. T is just a simple variable. It's just counting the number of trips in the loop, just to verify that the computation is correct. F is where all the excitement is. F is a foo that's made, and the foo is made by inheriting from an object which is a counter. So this counter has a method in it which counts down. So you call this counter has an initial value, you call this done method, it decrements the count and tells you whether it's 0. And I use that to control a loop, and I use it inside the loop. I calculate, I make an array of the same length of n, and in each element of the array I put the square of the corresponding n. And then the final thing, the reason I put this in at the end was you have this weird type system with 0 and null in the system, you know, which if you either have to tag, if you don't tag it, you're going to box it, boxing is painful, etc. So that was the point of doing that. When you break it all out, it sort of looks like this. Right? You're doing a set on an inherited array of an array element with, you get the array element and you do an addition and a multiply. Then there's the loop, and then the test at the end is an if, which is finding a count from an inherited slot and testing it against 0. So I showed you last week I had a Feeney implementation done in Truffle. I got that working to my satisfaction correctly about last weekend. And then I got a little help from Christian to tune this up using truffle techniques. So I did the obvious thing myself, which is I put in specializations for ints, which means all the computations are done on unboxed ints unless you mix types. We put in the inline caching for for all the dispatch. So Graal can do the inlining through all of the dispatching. We did the shape caching trick. So this is the idea of for each object you compute a shape which represents the names of the slots, and in addition what Christian did was he put the reference to a method slot as a shared attribute in the shape. So it's not in the object, it's in the shape, but they're shared, and so when you compare two objects for shape, if they have different methods, they're different. But if they have the same methods and the same slots, they're the same. And then what he did was the trick of combining the shapes down the inheritance chain to get a computed shape for the final one that summarizes all of the inherited information. So the methods are constants in the object shape, I just said there. I put in a specialization for int arrays. So if your array has nothing but ints, it's stored as a bunch of unboxed integers and it converts only to the boxed representation. If you store a non-boxed thing in. And Graal has a special way of doing while loops, which will make it easier to do on-stack replacement and using the Java while loops. I use that too. And we also did, using a substrate VM machinery, an AOT build and integration so that we ended up with a small binary that didn't need a JVM.
Sorry, my one quick question. You said the shape has the parent information as well.
Yes.
But in the actual value, is there still a link?
Yes. Yeah, when you make the object, the links are there.
Okay.
Turns out that that's not really a problem. So let me show you. So you got 200 instructions for your inner loop, 400.
But actually, that's with doing a bunch of static analysis that
Okay.
I basically figured that the cost loss is it's not a
So
law.
let me show you.
Okay.
This is a run of Graal. I made the loop run long enough that it would get Graal optimized. And somewhere down here, if I didn't just deselect it. God, it's hard to do this when you're looking at the side. Did I go past it? No, there it is. That's it. That's the entire loop as optimized. So one of the clever things is here, Graal escape analyzes the outer loop and aligns the object allocations. Only the array gets allocated, and the field slots in the object become scalars. So you're basically doing just array in multiplication. You're doing int multiplication, a summation into the array and the loop count. There's a safe point and the double increment because there's basically two counters in that loop.
Your line number jumps from 203 to, oh, is that line number?
No, these are addresses. These are nodes in some graph.
Oh, because
So
it
there's
jumps,
a bunch of data beneath
Yeah.
it's collapsed.
Yeah,
Okay.
exactly.
oh, because it jumps from 203 to 327. How long
Yeah,
is
well,
that
it,
line?
I don't know. Let's see what we've got in there.
That's one instruction.
No. It is one instruction, but there's some like.
See, this is just the metadata. There's some
Ah.
So I got it down. It's 13 instructions.
Okay.
It's 13 instructions. So I spent about a week building the basic implementation. Christian spent 2 days putting in the expert.
Have you tried running this against the Vectrons?
I've run it against the ones I have, but obviously not on the same machine, so I can't compare the times. But I have a runnable binary here if anyone wants
I
to.
mean, orders of magnitude should still be the same.
That's Sudoku.
It's in the same ballpark, right? It's just I didn't lose a lot of sleep. So Sudoku.
Order of magnitude.
It's a fairly big binary, so it takes a while to start up. So the very, very short running things are not super fast.
Okay.
Let me.
So I'm just curious about Sudoku though.
This is so hard to do and not seeing. Let me turn the mirroring on so I can see what I'm doing.
Yeah.
Did you guys do that code definition as well?
No, we
So how did you manage to not blow up your heap space for those pages?
We blow up.
for Vectron 4 we did.
Yeah.
We definitely blew up.
The rest are
For Vectron 3 we were sometimes
Benchmark for you blue. Oh, so you didn't.
we failed.
Okay.
We definitely blew up. We submitted knowing we were blowing up because we just was like that.
So who did benchmark 5 then?
Oh, Sudoku.
So benchmark 5.
For timing.
Oh, okay.
I did adjust benchmark for
Oh, that's the wrong one. That's the wrong
Just
one.
time.
It should not have blown up?
Should not have blown up.
You have to rule on previous time.
Oh, okay. Sorry, we have.
No, it's okay. I'm not in a rush.
Yeah,
Sure.
So,
It was a meeting at 5.
yeah, just get, we're gonna kick that.
Okay.
Hold over.
Let's see Sudoku.
Mini dash. This morning, Sue.
If you wish it, second order. You
Put
want
the time on it?
You want the timing?
I mean, most of these programs don't run long enough to do a decent compile. That's the real problem with our system.
Excuses.
Yeah.
Yeah,
Pretty good.
Pretty fast.
Fast.
Well, it's actually, when I looked at this last time, it was actually still compiling when the program.
Does it still run? Wait, does it still solve the? Does it still run the Sudoku solve?
Meaning what?
Meaning it's not reachable by the printf.
we don't eliminate anything that isn't connected.